Now let us move on to the next session. So we have one more speaker today, last speaker today. Then we'll all do hands-on session. Annapurna Padmavathy from Usmania University. So good afternoon, Padmavathy. Very happy to have you here.
Thank you very much.
So Dr. Padmavathy, she's currently a professor at Usmania University. She has completed a PhD from IIT Bombay. And she did few brief stints as a postdoctoral fellow at Emory University, Atlanta, USA, and Okazaki, Japan. Then she started her career as an assistant professor in the year 2007, and she has been teaching for last 20 years. And currently, she's a professor in Usmania University Chemistry Department. So let me continue. So Dr. Padmavathy has many research projects funded by UGC and DST, and she's also guiding PhD students, around 8 to 10 of them. So Padmavathy, over to you for your presentation.
Thank you very much. First and foremost, I would like to thank IIT Bombay in general and Professor Kannan, Sneha and all the team that has given me this opportunity to say something what I know little. Thank you very much for the opportunity given. And let me share my screen. So very good afternoon to all. I would like to talk a little about this common ion effect. And I think we are all, as teachers, we are familiar with this common ion effect. The principle behind common ion effect is Le-Chatelier's principle. So it says that whenever we deal with any chemical system of interest, and if you subject it to a small change in terms of temperature, pressure, composition of any of the components of the system, the equilibrium will shift in a direction either to nullify the change or reduce the effect. Okay, so this is the main principle behind common ion effect. So the common ion effect is nothing but an ion is common in between two electrolytes, and then because of the extra ion that is generated, there is degree of dissociation of one component decreases, and as a result precipitation would take place. So this is general phenomena we know. So the phenomena of lowering the degree of dissociation of a weak electrolyte when it is added to the solution of a strong electrolyte which has a common ion. So weak electrolyte and strong electrolyte should have an ion in common, then only precipitation would occur. This is what is our general knowledge or understanding about common ion effect. So let us see, we were saying earlier that it is mainly dependent and the phenomena is mainly involved in, the phenomena is application of Le-Chatelier's principle, and the shift in chemical equilibrium occurs due to solubility. Okay, so this occurs due to solubility, and it occurs solubility of the electrolytes. They play an important role in this. And this common ion effect has major application in analysis of chemicals as well as in industrial preparations. Mainly, it helps to increase the product formation. So the general applications that we are familiar about this is buffering of solutions, purifying salts, and salting out of soap, that is soap preparation, and precipitation of sodium chloride or any other salt, and manufacturing of baking soda, washing soda and others, and water treatment. See, this is what we are, immediately we can pick up the examples, but it can be applied to many. Okay, so let me, so first of all, we have two electrolytes, and solubility of the electrolytes play an important role. Let us know a little bit about solubility and how we can use this ChemCollective software that is available for us to know about solubility of a compound, and then we'll go further into common ion effect examples. So solubility, we all are familiar, it is dependent on temperature. And we know increase in temperature, automatically it helps to increase. Suppose we put little salt in water, you raise the temperature, it dissolves. Sugar, water, we are all familiar with these general examples. And if you have an ion in common, the solubility decreases. And if you have a salt, then it increases solubility. And pH anyway, it affects because we have ionic compounds. For example, if you take strong acid, strong base, weak base, they are all, we have H plus ions, which determines the pH of the solution. pH is negative log of H plus ion. And also, presence of complexing agents also play an important role in solubility. So this whole common ion effect is governed by solubility, and solubility in turn is dependent on what factors. So here I have taken an example. I hope it is visible here. So you take this chemical active software, and in this temperature and solubility of salts. So I've taken copper sulfate and then added copper sulfate to this 100 ml distilled water. So all of you, maybe you must have, some of you must have started today. So you will be getting a screen like this, and at the left hand side you have all this. So I have taken screenshots because some I have taken one video as well. So just I thought maybe this is more easy for us to follow it up, because
Dr.
we can keep
Padma?
slides side by side. Yeah.
Sorry to interrupt you. Can you show the one image by image, not 6 images in one slide? Because I think they're too small to make out what's happening in each one.
Okay, you are unable to see it.
You can show the
Okay, then
single separate images, individual images.
okay, let me expand it. Yeah, I hope now it is visible. Hello.
It's like two images are overlapping.
So let me make it slightly big. What about this? Yeah, because I have merged all. No, that's the problem.
Okay.
I will try to expand when I am talking about that particular slide. It is confusing.
Yeah, I guess so.
Okay, let me then add one more, just one. So this is what we get. I hope it is clear now.
Yeah, this is nice.
Yeah.
You
So
can
here we
full screen maybe.
Yeah. So here we have this copper sulfate, and we have picked up copper sulfate from this menu, and you have taken 100 ml distilled water. So you can add this copper sulfate to distilled water. That is what is we are trying to see. So initially we have a left hand side here. So this menu tells us about this is related to aqueous solution. So in this distilled water, when it is pointed out, you will be able to see what all are present. So H plus ions, this concentration, OH minus ion, this concentration, because we know ionic product of water is 10 to the power minus 7 into 10 to the power minus 7, that is 10 to the power minus 14, that is kW. So you can just click on this vessel, because I am not in online with the VLabs. So that is the reason why I may not be able to show you here, but I have one screen recording, so that may give you more information. So right now you please, I'm just telling about the solubility of the salt. So when you add this to this, so we can see whether it is exothermic, whether heat is released, whether heat is absorbed, that is endothermic or exothermic, can be obtained from increase in temperature or decrease in temperature, that can be seen here. Okay, that is one. And also when you add this copper sulfate to distilled water, then what happens is you have copper ions and sulfate ions that can be seen. So in the next slide, you can see copper ions and then sulfate ions also visible here. Okay, so and when you increase the temperature, what I would like to tell is, if you increase the temperature, then what happens to the solubility? Will the solubility increase or no? So what happens to this copper sulfate? So that is in some cases, rarely it decreases, but generally it increases. That is what I would like to show it here. So I'll close this and pick up another this thing, and so So I'll paste the one here and then. And also we can also note what happens to the pH as well. Here you have a pH meter. So if we are dealing with H plus ions, then you can also note what happens to pH. So here, when I added copper sulfate to distilled water, then you can see that, I mean, you have how many copper plus ions are there, how many sulfate ions are there, what is the molarity. Okay, concentration is reported. You can also click this button here, which will tell you, which will report the concentration in others. Okay, so I will just close this. I think I may be taking more time because I should have done it in the way it is more visible. So let me take the last one. So what I did is I tried to increase the temperature. We have a temperature scale. Thermochemistry related data will be there once you right click on this. Then if you can raise the temperature. So when you raise the temperature, here you can see 60 degrees centigrade. So if you raise the temperature, what would happen to the solubility? So that is what I have mentioned here. Okay, so let me go back to the slide. Hope now I will try to put this in. Yeah, now I think maybe you can just focus on this solubility data here and here and here. Okay, so what would happen, whether it has any effect or not. Then the similar thing is done for cerium sulfate. So what is observed in cerium sulfate is this is one of the salt whose solubility in water decreases with rising temperature. So if you keep on rising temperature, solubility decreases. So here it is 1 into 10 to the power minus 1. And here you can see some value into 10 to the power minus 2. So there is a decrease in temperature. So this is how you can check the solubility of the compound and then the effect of temperature, and also what happens to it when you, I mean, whether it is an exothermic or endothermic, all that can be studied by observing what happens in this, slide that is there right side. And we have various applications of common ion effect. So one is your semi-micro analysis or qualitative analysis of the ions that are there. And you can go for purification of salts. And then you can also go for this salting out of soap, that is preparation of soaps. And then in manufacture of sodium bicarbonate and sodium carbonate in Solvay process. In Solvay process, actually sodium bicarbonate reaction that results in precipitation, and as a result, common ion effect is important in this only when compared to preparation of sodium carbonate. Then we have water treatment, regulation of buffers. So ultimately, the point is we are dealing with electrolytes. Electrolytes have ions. We can have strong electrolyte or weak electrolyte based on the ability of the ion. You have its mobility, and then accordingly the one which is weak electrolyte in both, the weaker one will be suppressed by the stronger electrolyte, which is, I mean, electrolyte ion which is in common. So this is the main principle, and we follow it up in the next few slides. So the first one is the shift in equilibrium caused by the addition of a compound. This is your Le-Chatelier's principle. Dissociation of weak acid. Okay, so let me show you this weak acid, acetic acid, and then it is dissociated into CH3COO minus and H plus, and this is weak acid, and this is the corresponding one is a strong salt, sodium acetate. This sodium acetate dissociates completely, being a strong salt, it completely dissociates into acetate ion and Na+. So these two have something in common, that is CH3CO minus. So using this common, you can shift the equilibrium towards left. Suppose you add sodium acetate, it immediately dissociates. So there is excess of ions that are generated. So because this is in equilibrium, it tries to maintain its equilibrium always constant, this acetic acid. So what it does, the equilibrium shifts to left, and as a result, this CH3CO minus, so equilibrium shifts to left. So here you can note this addition of small amount of a strong electrolyte such as CS3COO-Na, sodium ethanoate, to the aqueous solution results in the dissociation of the former. From the above, it follows that ethanoate ions are common in the preparation, so their concentration in the solution will increase. Okay, so this is governed by your Le-Chatelier's principle, because anything that is added in excess or some change is done, I mean, it tries to re-establish to its previous state. So that because of this common ion, there is reduction in solubility of acetic acid. And then same is the case with weak base. We have ammonium hydroxide and then ammonium chloride. There is ion which is in common, and this common ion that is there, it reduces this solubility of ammonia in water. So here in this, I have taken the solution acetic acid, and then I try to take this 250 ml of Erlenmeyer flask and then try to dissolve this acetic acid in this. Okay, and then sodium acetate also I have taken. So I tried to pick up in the previous whatever experiment I was trying to tell, acetic acid is taken, sodium acetate is taken in both the beakers, and we were trying to add this sodium acetate to sodium acetic acid, that is acetic acid. So I am trying to add sodium acetate to acetic acid and see what happens. So that is what is this experiment. Yeah, so sodium acetate is here and acetic sodium acetate, and this is 1 molar acetic acid. So I have taken acetic acid and then added sodium acetate to it. Then you can see what would happen to the pH and what would happen to the dissociation of the ions. See here, you just I've taken these two acetic, just look at this. This is only acetic acid is there. Acetic acid is dissociated into CS3COO minus and H plus. You can see the concentration, or the, I should say it is not, we can say it as solubility. And acetic acid is showing 2.38 as pH. Okay, now let me add sodium acetate to this. So in this slide, I have added sodium acetate to this, and you can see what happened to the suppression of the dissociation of acetic acid. So here acetic acid is in the order of 10 to the power minus 1. Here it is of the order of 10 to the power minus 5. So there is decrease in dissociation of acetic acid. So that is what we are going to show from this slide. So, and you can also see the pH. The pH reached 9.38. Okay, so similarly, we can also work with ammonia, and then ammonia, you dissolve ammonia, 3 molar ammonia is taken. You dissolve it in, 250 ml standard flask is taken, which has distilled water. You can add some distilled water. I randomly took the amount, but even then it works. So you take some amount of water, make sure, the concentration is high. Okay, so 3 molar ammonia is added to this. I think I have taken some around, it is given here 20 ml. So I have taken 20 ml of water and added ammonia to this. And you can see what happened to the dissociation of ammonia plus water. So when you add ammonia to water, what happens? You get NH4 plus and then OH minus. So then you can see what is the pH. The pH is, it crosses 7, it is in basic region, around 12. And now you can also look at the temperature simultaneously. There is a temperature scale here, that you have ions here. So all this can be monitored carefully so that you will be knowing what is happening when you mix two solutions. Okay, so ammonium hydroxide, actually ammonical water is this. Then for that I have added ammonium chloride. So when you have added ammonium chloride to this, what happens? We know that ammonium ion is in common. So there is the suppression of dissociation of ammonium hydroxide. So as a result, ammonia plus water, okay, as a result, you have a decrease in your pH. So earlier you can see the increase in pH 11.71. Here you have a decrease in pH 4.63. Okay, so this is how you can come to know about the common ion effect, study on common ion effect. So I'll just go back to this slide. Weak base, ammonium hydroxide, it is dissociated into ammonium plus ion and then OH. Ammonium chloride, okay, is added. When you add an amount of ammonium chloride, then what happens is the equilibrium will shift to back and you have the formation of ammonium hydroxide. Okay, so ammonium hydroxide, when dissociated, you have 11 point some pH, and then that is in basic region, and it shifts to, it decreases when you add ammonium. So this is what is an example related to the addition of, a base, about a base added and about an acid. So you add a strong salt to acetic acid and you add ammonium chloride to ammonia. Okay, and then see what happens using this labs. It is as good as your lab experiment that you do in laboratory offline. Yeah, so like we are saying that when you add something, that is a decrease in solubility. Actually, in the last minute I added this. So how much there is a decrease in solubility when you add an ion in common? Okay, that is the example I'm going to show here. So we have silver chloride. Okay, silver chloride, it dissociates into silver plus and Cl minus ions. So we know the solubility product, that is x square, which is given as 1 into 10 to the power minus 10. So now to this you are adding sodium chloride. We add sodium chloride. Silver chloride has Cl minus ion. Sodium chloride has chloride ion, which is in common. So when you add sodium chloride to silver chloride, what is the decrease in solubility? So that can be observed from solubility product in your theoretical calculations. So here we have the solubility of silver chloride, solubility product is given as 1 into 10 to the power minus 10 at 25 degrees centigrade. So you take the square. So Ag plus into Cl minus ion whole square is 1.0 into 10 to the power minus 10. So you get the value as 1 into 10 to the power minus 5 moles per liter. Right? This is your general solubility. Now, when I add sodium chloride to this, what would happen? So when you add 0.1 molar sodium chloride, so you just you have added little bit of chloride ion, right, from sodium chloride. So as a result, there is increase in concentration of Cl minus. So here in this problem, the increase is 0.1. So when it increases by 0.1, so your solubility product now is y into y plus 0.1, which is equal to 1 into 10 to the power minus 10. So now if you rearrange this, you will be getting y is 10 to the power minus 9. That is 1.0 into 10 to the power minus 10 divided by 0.1, which comes to 10 to the power minus 9. Okay. So 10 to the power minus 9 is your y value. That means after addition of sodium chloride, it has come to 10 to the power minus 9. Earlier it is 10 to the power minus 1. So you can see how much decrease in solubility occurred because of this common ion or ion in common. That is what you can understand from this calculation. Okay, so now the conclusion is when a new substance having a common ion is added to an already saturated salt, there is a reduced solubility. So here till now we are talking of acids and bases, and you add ion in common. Apart from that, you can also add a salt which has an ion in common. So let us look at this. This is suppose we all are familiar with preparation of your common salt. That is sodium chloride preparation. Like in from seawater, we prepare sodium chloride, and you can imagine that and how we want to prepare a little bit of sodium chloride from that. So we know sodium chloride is your common salt. It is dissociated into N plus and Cl minus. Okay. The passage of pure, if you add hydrogen chloride gas to this, then what happens is because of common ion, Cl minus is common. As a result, the sodium chloride will be precipitated. So the passage of pure hydrogen chloride gas through the above solution undergoes complete dissociation and results in an increase in the concentration of chloride ions. This causes a shift in equilibrium towards the left, okay, accordance with Le-Chatelier's principle. Thus, dissociation of sodium chloride is suppressed and pure sodium chloride is precipitated as sodium salt. Okay, this is what. So for this, we are trying to do an exercise. So first of all, we need to prepare a saturated sodium chloride solution. So a saturated solution is a solution in equilibrium with excess solute. I think we are familiar with this. So now sodium chloride solubility in grams per 100 grams water is approximately 36 grams. So what I do is I weigh 36 grams of sodium chloride and I dissolve it in water and prepare a saturated solution. So after preparation of saturated solution, then what I do is I transfer some amount of HCl to this. So 11.6 molar HCl. That means high concentration of HCl, because we are passing here gas, right? Pure hydrogen chloride gas. That means it is highly concentrated. So we'll take whatever in our solutions, whatever high concentration solution is there of HCl, we pick that up. And then we transfer that HCl solution into a beaker. Okay, so what I would like to tell you is here, I mean here I just want to show you that sodium chloride is getting precipitated. Okay, our goal is we are preparing common salt. So to prepare common salt, we pass HCl gas through it, and then we get solid sodium chloride. That is our goal. So now, I mean, what is available with us? We take sodium chloride, we prepare a saturated solution of sodium chloride. So we prepared 40 grams of sodium chloride in 100 ml water. Then to this, HCl is added. I will show you the video clipping, but before that, I just want to explain. So 40 grams of sodium chloride in 100 ml water, you add now HCl solution to this, which is having 11.6 molar. So when you add this, what should happen according to this rule? This sodium chloride should be precipitated, right? Because of the common ion Cl minus. So then here we should get in the, when you click this solid radio button, you will be able to see the precipitation of sodium chloride. So that is what we can see here. So let us look at the video. So this is, so 40 ml of HCl is taken, 11.6 molar, and it is added and it is kept aside. And then you click the solid radio button, and you can see the sodium chloride 4.33260 has been precipitated out, right? This shows, and you can also see the pH. pH is showing 0. So when you have 0 pH, that shows it is neutral. Like, sorry, it is giving us 0 value because sodium chloride is unable to detect the value. Actually, when you have water along with sodium chloride, you will be getting 7 pH. Okay. So this is about, purification of common salt. So like that, you can purify other salts as well. Let me, I think it is still working. You can see the concentrations also here. And what would happen when you are clicking on it? If you click on, say, one beaker, it gives the details of that. So when you click on a particular flask, it gives the details related to the flask. So this is how one can purify, common salt here. And then we learned only about sodium chloride. You can think of potassium chloride and all other salts that are generally available, and they can be purified using this concept of common ion effect. So actually, we can also think of this common ion effect in the preparation of soap by hydrolysis of oils. So we know that soap are sodium salts of fatty acids, right? So you have this RCONA, and in our daily life also we can see the precipitation of soap in hard water. So when we use hard water, because of common ion effect only, it just precipitates and goes away. So the addition of common ion to a saturated solution of a salt causes the precipitation of the salt. So here we have this sodium salt of fatty acid, which is coming from soap, and you add small amount of sodium chloride. Then what should happen? You have an ion in common. Because of ion in common, it should be precipitated out. So the soaps precipitate due to a combination of common ion effect and increased ionic strength. So solid soaps are recovered from soap solution by addition of salt, such as here, if you have sodium in common, sodium salt. Okay, potassium salt. So we know precipitation occurs when ionic product exceeds solubility product. Okay, so this is one example. Similarly, in Solvay process, actually the problem I had is when I have to take the compounds related to these experiments from this, some are missing. So that's the reason why I couldn't do complete justice to all the applications of common ion effect that I'm going to show here. But then I would like to request all the participants to take these examples, and then you can replace if you don't have, because there is no potassium chloride in one slot. Like potassium chloride is available in some other place, so we couldn't pick that potassium chloride salt into another workbench because there is some restricting wall to take the compounds from one place of workbench to other. So that is the reason why I try to limit myself only with sodium chloride, because that I could get. And I'm sorry for that, because I couldn't do complete give complete information related to all the applications that I'm going to show you now. So another application is sodium bicarbonate. So they're there, all these are there, but they're scattered. That's a problem. So we know that this sodium bicarbonate is baking soda, and in solvay process, sodium carbonate is prepared. But then you go for, this common ion effect is applicable in the preparation of sodium bicarbonate. Okay, so common ion effect is observed in preparation of sodium bicarbonate, but solvay process deals with preparation of sodium carbonate industrially. The common ion effect is used in maintaining the buffer of ammonia and ammonium chloride when the brine is precipitated as sodium bicarbonate. So brine is your sodium chloride. So sodium chloride, you maintain this buffer, and as a result, sodium chloride plus carbon dioxide plus ammonia and water gives you sodium bicarbonate. The overall reaction, actually, it is a complex one, but the principle is that once the saturated solution of brine, that is sodium chloride, is saturated with ammonia and carbon dioxide, sodium bicarbonate will be precipitated from the solution because of your common ion effect. And sodium bicarbonate is generally soluble in water, but its solubility sharply decreases in a concentrated solution of sodium chloride, and thus causing sodium bicarbonate to precipitate. So this is solvay process, and so this is sodium chloride brine solution. Okay, and then you allow this ammonia and then carbon dioxide to seep through, and finally you have the precipitation of sodium bicarbonate here. So saturated solution of sodium chloride is taken, and it is saturated again with ammonia and carbon dioxide, which results in precipitation of sodium bicarbonate. Yeah, then I think we all are familiar with this hard water, and then soft water, it's easy to handle, but when it comes to hard water, we know that we use ion exchange resins nowadays to remove. And then we can also go with common ion effect is the main principle involved in this precipitation of calcium and magnesium salts as calcium carbonates and magnesium carbonates. So this common ion effect is important for us in general physical chemistry and in analytical chemistry for semi-micro analysis mainly. So let us go through it in qualitative salt analysis. So in group 2, we have this sulfide, we generally copper, lead, and these are precipitated when hydrogen sulfide gas is passed through the original solution. So we all know how to prepare. We are given salt, and then you prepare some original solution using sodium carbonate extract, and then you take the original solution wherein you have the unknown ion, and then you pass H2S gas. So when you pass H2S gas in presence of HCl, then this will be precipitated. And once it is precipitated as the corresponding salt, suppose you have copper sulfide, and then lead sulfide, like this it gets precipitated, and then you will be able, this is simple Le-Chatelier's principle, the equilibrium will shift to left, and then in the presence of a common ion. So here you have H plus and HCl you are adding, right? So this has ion in common, so it tries to precipitate this H2S. It tries to precipitate sulfur S2 minus. S2 here, I think I should have 2 minus. This 2 has come down, sorry for that. So here also the same, S2 minus. So this will be precipitated as copper sulfide or lead sulfide. So the same is valid when you go to the next group, that is group 3. So here, instead of H2S and HCl that you are using, here group 3 cations are precipitated as hydroxides by ammonium hydroxide in presence of ammonium chloride. So like actually here you must have noted when you are doing this experiment, aluminium, iron and chromium, in these 3 cases they are precipitated, whereas zinc, nickel and cobalt are in this. As a result, they are precipitated, whereas the cations of this zinc, nickel and cobalt, they are not precipitated because they have higher solubility product. Then we have group 4, and group 4 sulfides have higher solubility product, and they are precipitated by hydrogen sulfide in presence of ammonium hydroxide. So we have hydroxyl ion coming from NH4OH, and this combines with hydrogen ion of H2S to form water, and then the removal of H plus from the product shifts the equilibrium to the right. So you have cobalt sulfide, nickel sulfide and zinc sulfide precipitated out. So so here what I would like to conclude is, it's an important phenomena, common ion effect, and it is one of the major factor that affects the solubility of substances, and it is established that the present common ion on an equilibrium reaction system can affect solubility, and it can help in precipitation. So this like whenever we want something to be precipitated, you can use this concept of common ion effect and your Le-Chatelier's principle mainly to work on your requirement and problem. So common ion effect appears to be a regular occurrence in many processes. So it can be used for extraction of salt from seawater, purification of salts, like qualitative analysis, like our semi-micro analysis, water treatment, and then soap manufacture, regulation of buffers, because pH will be there, right? So regulation of buffers and precipitation of useful ingredients for food and pharmaceutical applications. So actually lot of things can be done for applications of common ion effect. We need to explore, but then this is all I could exchange or share with you right now. So I mean, we need to understand it better and execute better so that we can come with a proper and right solution. And this is all. Thank you very much for giving me this opportunity to express myself on common ion effect.
Thank you so much, Dr. Padma, and your talk on the common ion effect was very useful, and how the common ion effect experiments can be done in ChemCollective virtual labs, that also you have shown. But there are tutorials also where we have explained this. So I think our participants will do it later in the day today. The experiments on the solubility and common ion effect, and they will get benefited by your talk. Thank you so
very much. Thank you very much for giving this opportunity. Namaskaram, sir, Kannan, sir. Thank you so much.
Yeah, and I would like to also say that
yeah,
Dr. Padma attended the advanced workshop on ChemCollective virtual labs. Now she's an expert. She's using it for your students also.
Yeah, I think I have taken this message last time when I attended, that I should disseminate this knowledge to all the people who come around. So I think I'll try to do the best I can. Thank you very much, sir.
Thank you, ma'am. Thank you so much.
Thank you.